All right, welcome back. So here's the result of my training. The last time I decided to run for 100 epochs, and that's with all of the modifications that we made, all the augmentations to our image. And you can see here that my in yellow or orange, the validation continued to increase, and it kind of correlated with the training, which is good. And similarly, our loss function kind of is doing something like that, which is good. What we're trying to avoid is a situation like we had the first time where, if you remember, did something like this and then it kind of stalled out and it kind of maybe did this. So what that meant was, we started to overfit. Our training was getting, perfectly matched to the, to the training data, but it was starting to become less generalizable. Validation images were no longer correlating to that because it was picking up things that maybe weren't really there, like we talked about. And the same thing here, we saw something that kind of looked like this. So it looks good. So I'm going to actually push this to, I'm going to push this farther. Maybe I'm going to go to 200 epochs just for experiment purposes. We'll see how it looks, see at what point we start to overtrain, if we start to overtrain. And I'm going to skip ahead. And then afterwards, we're going to update our predict.py file. We're going to make it more interesting for going through lots of images, maybe in a folder. We could dump a bunch of images in there that we want to predict, and we can use OpenCV to label them. So we're going to do that. I'm just going to skip ahead and show you the result of 200 epochs of training. So I'll see you in just a moment. Okay, so I just finished 200 epochs and actually got an interesting result here. So if we look at our validation loss curve, like before out to the 100 epochs mark, that got clipped off a little bit, but let me go to the image here. You can see out to about the 100 epochs or so where we ended the last video, or the last section, the training kind of correlates, but now you can see how it's starting to do this and it's starting to flatten out while my training is continuing to get better, less loss. So I would say that right around that 90 to 100 epoch point is actually where the model probably starts to hit the overtraining point. So you can kind of see that phenomenon. It's a little less apparent in the accuracy, but you can see the accuracy is increasing, but then it starts to basically level out. So if I jump over to the drawing here, you can see how the accuracy is getting better, and then right here, which is probably around that 90 or 100 mark or so, it starts to get really flat in this region here. You're starting to see lots of this stuff versus the blue line, which you can see is still getting better. So that makes sense because our training data, we're training on that over and over and over again. So we're starting to exactly match the training set, but the validation data, it's not generalizable, so it's not working on other pictures that aren't in the training set. So long story short is it looks like for my configuration, I would say somewhere around here is kind of where the model, somewhere in this region is where the model kind of hits that overtraining point, and anything past that's not really good. Now if we wanted to get this to, let's say, the 90 or 95 or 97 or 99% accuracy, we'd have to go back probably and add some changes to our augmentation layers, add more images. Maybe there's different types of images that we would want to do to make this more generalizable. So we'd want to go back and make some adjustments to our model. But I think at this point I would say that we have something that's reasonable. We're probably going to get around 85, somewhere between 85 and 90% accuracy, which is still pretty cool. So let's go ahead and actually build our prediction boilerplate code that's going to let us kind of quickly iterate over many images for predictions. So let's do that now. Okay, so next we're going to implement a change to our predict.py. So go ahead and delete everything under the main, the running section here. Just delete all that. And we already have some other stuff that we've used previously, so this looks good. Add one additional import called import pathlib. We're going to be using pathlib. That wasn't in the file previously, and we've already talked about pathlib. So what we're going to do is we are going to first load our model in, of course. So we'll say model equals to load model, and we have to put in our model path. So I'll put a variable in here, and I'll say my model path equals, and in my case I'm going to use the previous one, not the one I trained for 200 epochs, because I believe that's overtrained. So that's going to be ./models/model_3 in my case. So make sure you have your correct model. And then what we're going to do is we're going to get our images. So we're going to say data dir equals path lib dot path, and we're going to put in the path to our test images. So in my case, I'm going to store all of my test images in test_image. So we'll say that's ./test_image. So that will get all of the items there, and then we can say images equals to data dir dot glob, and then we could say here star.star. So every file in there. This is useful. So for example, if we had a text file in here, we wanted to filter that out, we could use the glob here to change this to example, just get JPEGs or whatever we want to do. We'll just get everything, since we're just going to have images in there for now. So that's pretty easy. Okay, next what we want to do is we want to iterate through all of our images, and we want to manipulate them, predict on them. So we're going to say choice and score equals to image predict, and we have to pass in our model, and we have to pass in our image. Okay, whoops. For image in images. We want to do this for every image in our images. Remember, images will give us a list of all those items, all those image paths. So we're going to pass in all these image paths, and we're going to pass in the model that we've just loaded. So I've loaded my model number 3. That will give us our choice, which is going to be the choice item, and it will give us a score. And it will obviously print this out for us for every image, just as a convenience thing. Okay, so that's going to give us the prediction. So we can run this real quick and just see if it's going to pick up rows.jpg. Make sure we don't have an error here. Okay, so it's predicted it as a tulip with 71.33, so not a great start, but we'll try another image, so hopefully that'll be better. And then what we want to do is we want to also, let's actually display this with OpenCV now. So we'll say temp equals cv2.imread, and we'll put in our image as a string. Convert that to a string. That'll just make that work properly. So this will load that image into OpenCV. And then what we could do is we could show that right now, but let's actually add some things to it. So I'm calling this image as temp. So we're going to say cv2.putText. So this function will add text to an image. And the first one is it's going to take an image matrix. So we're going to pass back in our temp image. We're going to pass in the text as our choice. So whatever it's selected, that's going to be the choice. And then it's going to ask us where do we want to place that, where the origin is. So we'll just say 35 by 35 pixels from the top left-hand corner. It's going to ask us for a font. We can say cv2 dot, we'll say font, sorry, I know you guys can't see this, dot font, let's see here, cv2 dot font underscore Hershey underscore duplex. This is the one I usually use. You can change these to whatever you want. Put in a size 0.8. Put in a scale or a color, so we'll make this red, so 00255. Remember, colors are BGR, not RGB in OpenCV. And then we've got a thickness, we'll say 1. And then anti-aliasing, we'll say cv2.line underscore AA. So that's going to take this image, read it into memory, and then it's going to make this modification. It's still not going to display it yet. We also want to display the confidence number, not just the selection. So we can actually say that our confidence, conf, equals np.max score. So whatever the maximum was, that's the number. And then we can copy this, and we can add the confidence score to that image as well. So we're going to put it back on the temp image. So we're going to keep that the same. This time, though, instead of putting the choice text, we're going to put the confidence. and we want to convert that so it's instead of it being a huge decimal number, we can actually use a formatted string. So we'll say it's conf times 100 to convert it into a percentage, and then we can say 2 decimal points. And then we need to move this down a little bit. We don't want it to display in the same location. So we'll move it down additional 35 pixels, and we can leave the rest of these options the same. Okay. Oh, looks like I've got an indentation error here. So let me fix that. There we go. So I have this. So I'm calculating the confidence as a number, and then we're going to put that text on this temp image by converting it to a percentage by multiplying it times 100, and then two decimal point precision for the printing. And then after we do that modification, we'll do cv2.imShow. So this will show our image. We want to give this a name first. So the first argument is a string for the name. So we'll say that's the string of the image. So just the file path will be the title of this window. And then we want to put in our temporary image. And then finally, we want to make sure that that doesn't appear and disappear instantly. So in CV2, if we ran this, it would execute and immediately close that. We want to hold that window open. So we're going to say cv2.waitKey 0. This will cause OpenCV to wait until a user presses a button. Once a user presses a key, it will then continue with code execution. And finally, we want to destroy all windows after we do that. We don't want to leave windows open between images. So let's run this code now. Okay, so you can see that it is saying it's tulips with a 71.33, and if I hit a key, it'll disappear. Let me actually do one more thing, because that's kind of a large size. We can actually scale this down. So we can say temp equals cv2.resize, and we'll put in our image temp, and we'll put in we can resize this to, let's say, 180 by 180. So this would be the image size that, I believe it's 180 by 180, yeah. So it's the image size that went into our model, just so we can resize it. Let's do that again. So this is the size of the image that went in, tulips with 71.33. So it looks like our prediction pipeline's working, but let's make this bigger. Let's not make it so small. Let's make it maybe a 500 by 500 image. Run this one more time. We could obviously keep the original proportions of the image too and just scale it proportionally, but I'm just throwing this together quick. So there you go. Tulip 71.33. We can add a percent sign there to make it display the percent sign. So I'll run this one last time, and then afterwards let's take a bunch of images off the internet and let's try them out. So there you go. So it looks like our prediction pipeline is working now. So we're able to see the image tulip 71.33. Obviously that's wrong. This is rose, but let's try it on some additional images since our model is only about 85% accurate, or at least that's what it appears to be from our training. So I'm going to pause the video now. I'm going to download about a dozen images or so, and then let's try them, and I encourage you to do the same. So I'll see you in just a moment. Okay, so I've got a group of images here. I've got a couple of pictures of dandelions, daisies. I tried to get two different dandelions, the seed version and the regular version, like this one. I got some roses. This was the rose that we had trouble with before. We have another rose here, sunflowers, tulips, and let's predict on these. And there was actually a small mistake in the code. Make sure you tab this over because we want to do a while loop here. So it was like this, and we want to show the image for every image. So we don't want to just predict and then just show the last one. So tab all these over. All of these should be in the while loop, or not the while loop, sorry, I guess the for loop here, the for image and images. And then lastly, unindented have destroy all windows, so that we do destroy all the windows at the end. So just tab that over, and let's run this. And you can see, okay, that we got our first image. This is a dandelion with 100%, so that's a good result. And we have tulips here. Oh, let me do one thing with the code. Let me tab this over. I don't want to keep all the windows open on every iteration either. Let's run that again. So now when we hit a key, it should destroy those windows and we can proceed. So we have our dandelion, 100%, looks good. Okay, now we've got a tulip, 66%, that's correct choice. So again, rose, it's confusing rose and tulips for some reason. Dandelion, good. Okay, this time it got roses right, so we got roses, 98%, looks good. Tulips, 81, good. Daisy, 100, good. Sunflower, 99, good. And again, well, this was the image we had before, the tulips. And then, okay, Daisy, 99%. Sunflowers, 100%. So it looks like it got all of the new images. It's having the most trouble with roses right now. So this image was what we had before. It called this tulips, and it got this one correct, and it got this one wrong. It thinks these ones are tulips. So pretty good accuracy with so far, on the small test data with daisies and dandelions, but there's probably some optimization. Maybe it has something to do with colors. Maybe we need to add some additional augmentation. Maybe we need a little bit more of a data set on daisies on roses and tulips, so we can try to capture the differences between roses and tulips. At first I thought maybe it was having trouble because a lot of the tulip images show the tulips kind of vertical, and the roses kind of the same, where they kind of have this vertical shape, and they kind of have a relatively small flower and then like a stem, compared with like a sunflower, which is round, really wide, or daisy, lots of points, or lots of leaves, or petals, I guess I should say. So I'm guessing that there's some optimization to be done there. Also, tulips, a lot of them are red, so so I would say tulips and roses maybe are a little bit harder to differentiate logically than trying to differentiate like a daisy and a rose. That's a lot easier of a differentiation. But congratulations, you just finished your first TensorFlow model. We have something that's about 85% accurate at predicting flower species between these 5 species. So congratulations and great job. You should be very proud of yourself. And I hope to see you in some future videos. So like and subscribe, and hope to see you again soon.